Okay, this is the second rule, which is known as the Lin rule. It says that the integral of f prime x over f of x dx is equals to ln of f of x plus c. So in simple terms, it means that in order for you to be able to use this rule, you must check if the numerator is the derivative of the denominator. Then you can apply the rule. If not, you are always allowed to manipulate as long as you'll be able to take it back to its original form. Now let's look at this example. It says find the integral of into 3x squared plus 4x all over 4x cubed plus 8x squared dx. Right. So in this case, separate your variables. Your f of x is equals to what? It is equals to 4x cubed plus 8x squared. Now the derivative of this would be 12x squared plus 16x. Now you need to rewrite this equation in a correct form. So it's the integral of f prime, according to what we wrote there, it is 2x squared plus 16x all over 4x cubed plus 8x squared dx. Now, how do we take it back to its original form? Right. So to take this numerator back to this 3x squared plus 4x, we have to multiply by 1 over 4. Right. Then we can apply the rule. So it's going to be 1 over 4 ln of f of x. In this case, our f of x is 4x cubed plus 8x squared, close brackets, plus c is the answer. Right. C. Look at the example number 2. And the integral of into 18x minus 3, close brackets, all over 3x squared minus x plus 2. Right. Dx. Again, what is your f of x? F of x is 3x squared minus x plus 2. Right? So our f prime x in this case would be 6x minus 1, because derivative of a constant is 0. Then we have to go back to the equation and rewrite it in a way that will satisfy the rule. So our f prime according to our solution is 6x minus 1 all over 3x squared minus x plus 2 dx. Now, how do we go back to this original form? So obviously we need to find a common multiple for this numerator in order for us to go back to here. So obviously, in order to get 18, what can I multiply 6 with? I can always multiply 6 with 3. So it's more like multiplying by 3 over 1. So 3 times 6 is 18. 3 times 1 is 3. Right. Now you can apply the rule because it is satisfied. So it's going to be 3 ln of 3x squared minus x plus 2, plus c is the answer. Right. So that's how you apply this rule. Let's see if we have another example. Okay, let's look at example number 3. Example number 3, find the integral of cos sec square 5x all over 1 plus cot 5x dx. Right. So let's see. What is our f of x in this case? Our f of x is equals to 1 plus cot 5x. Right. Now, the derivative of this would be equals to, what is the derivative of cot? Derivative of cot is negative 5 cosec square 5x. Right. Now we go back to this equation and write it in the form that will satisfy the rule. So this will be negative 5 cosec square 5x all over 1 plus cot 5x dx. Now how do I get rid of this minus 5? I have to multiply by negative 1 over 5. In that way, when I say minus 1 over 5 times 5 takes me back to the original equation. Then you can apply the rule. Negative 1 over 5 ln of f of x, in this case it's 1 plus cot 5x close bracket plus c is the answer. I do think that this rule is the easiest and the simplest out of all of the 4 rules that we're going to be dealing with. Right. Let's see if I have a space for one more example. Right. Let's see. Number 4. This is the last example I'm going to be doing. So it's the integral of dx over x ln 2x. Right. This can be written as equals to integral of 1 over x over ln 2x dx. Right. Then our f of x in this case is equals to ln 2x. Now what is the derivative of this? The derivative of this will be 1 over 2x times 2. So that 2 cancels this 2, right? So therefore derivative will then go back to 1 over x, right? Then we check. The numerator is actually the derivative of the denominator, so we can just apply the rule. So the rule will be ln of ln 2x close brackets plus c as the answer. Right. I hope you understand. So this is the second rule of the integration by inspection. Right. So our next slide will be the third rule. Right. And the fourth rule in the same slide. Thank you. Please don't forget to subscribe, and I hope you understand. Bye.